Hi guys, so in this video I'm going to be explaining all the shapes that we need to know as well as briefly going over intermolecular forces or IMF. Each shape is going to be represented in this format: A, X, N, E, M. A is a central atom, X is an outer atom, E is a lone pair on the central atom, and N and M are positive integers. So the first shape is AX2. You're going to need to know how to draw the Lewis structure to find out the shape. So you can see that there are 0 lone pairs on the central atom, so the angle between these two bonds is going to be 180 degrees. So you have to know one bond angle for this shape, 180 degrees. Hybridization is sp. This depends on how many electron regions there are. Each bond is one region, each lone pair is one region. So 2 regions is going to be sp hybrid orbitals. The polarity is nonpolar because 2 equal opposite vectors are going to cancel out. The net dipole is going to be equal to 0, so it's nonpolar. Next shape, AX2E, an example here being SO2. We drew one of the resonance structures here for SO2, and you can see that there's one lone pair on the central atom. This lone pair is going to repel these two oxygens, so they're going to be slightly closer together, and the angle between them is going to be slightly less than 120 degrees. It varies from compound to compound because of the lone pair. Hybridization is going to be sp2 because 3 electron regions, and it's going to be a polar shape because 2 vectors that look like this are never going to cancel out. The net vector is going to look like this. Net dipole is not going to be equal to 0, so it is going to be polar. AX2E2, you can see it's the same as the previous shape except for 2 lone pairs on the central atom and extra lone pair on the central atom here. And so this is going to repel these 2 outer atoms even more, so they're going to be closer together, and the angle is going to be less than 109 degrees. Of course, it varies from compound to compound, but for H2O, you need to know that the bond angle is 104.5 degrees, and the hybridization is sp3 because it's 4 electron regions, and the polarity is polar because 2 vectors that look like this are never going to cancel out, so the net dipole is not going to be equal to 0, so it's going to be polar. I forgot to mention the last shape is called V-shaped or bent, and this is also going to be V-shaped or bent. Next shape is going to be AX2E3, which is linear. You're going to need to know one bond angle, which is approximately 180 degrees. If you draw the Lewis structure, it's going to look like this. It's a bit hard to represent it, but these 3 lone pairs are actually perpendicular to the plane and they form a triangle. So the angle between each lone pair is 120 degrees. And these lone pairs are going to repel the outer atoms in such a way that the angle is approximately equal to 180 degrees. You can't be exactly sure because of the lone pairs. Hybridization is going to be dsp3 because 1, 2, 3, 4, 5 electron regions. But if it has D in it, you don't need to know it. So this is just for your information. Polarity is non-polar because of the linear shape, but since I3- is an ion, this will be polar. But if an atom has this format, it will usually be polar. If a molecule has this format, sorry. So moving on, the next shape, now we have 3 outer atoms instead of 2, AX3. An example is any compound with aluminum or boron, since there are exceptions to the octet rule and only need 6 electrons around them. So if you can see here, there's going to be a 120-degree bond angle between each bond, 120, 120, 120, and there's going to be 3 vectors that look like this, and they're all going to cancel out. The shape is triangular planar. One bond angle you need to know 120 degrees, and since you have 3 electron regions is sp2, and since we already said the net dipole is going to be equal to 0, so it's going to be a non-polar shape. Next shape is AX3E, which is trigonal pyramidal. You're going to draw the Lewis structure, and you're going to notice that there's one lone pair left on the central atom. So this is what the Lewis structure looks like, but this is what the shape actually looks like to help you visualize. So you're going to have 3 vectors going up like this, and the net vector is going to be like this. I know it's a little bit hard to visualize it because it's 3D, but these is actually a triangular base, and they're all connected to this N. So it forms a trigonal pyramidal shape. You need to know that the bond angle is less than 109 degrees. In the case of ammonia, NH3, the bond angle is 107 degrees. Hybridization is sp3 because there are 4 electron regions. And of course, it's a polar shape because the net dipole is not equal to 0. Next shape, AX3E2. is the same as the previous shape except for a second lone pair on the central atom. An example of a molecule that has this shape is a halogen bonded to 3 other halogens. So for example here we have ClF3. The Lewis structure looks like this, and these two lone pairs are going to repel these two outer atoms, but this outer atom is also going to repel these two outer atoms, so the shape is going to be a T. This is the bond angle between each F is approximately 90 degrees. The bond angle here is 180 degrees. You just need to know that the bond angle is 90 degrees approximately. Hybridization is dsp3 because 1, 2, 3, 4, 5 electron regions, but of course you don't need to know that for the exam. And the polarity is polar because these two vectors are going to cancel each other out, but this vector will not, so you're going to have a net dipole vertically downwards that's not equal to 0, so it's going to be a polar shape. Next shape, AX4. Now we have 4 outer atoms. An example is carbon bonded to any 4 atoms or NH4+. So carbon bonded to any 4 atoms, this is what the Lewis structure looks like, but this is what the shape looks like. It's very similar to the trigonal pyramidal, except it looks like this, as opposed to the trigonal pyramidal, which looked more like this. So the shape is tetrahedral. You need to know that the bond angle is exactly equal to 109 degrees, and hybridization is sp3, and it's a non-polar shape because these 3 vectors are going to add up to one net vector, which is going to cancel with this vector. Net dipole is equal to 0, so it's a non-polar shape. Hybridization is sp3 because 4 electron regions are on the central atom. Next shape, AX4E. It's the Lewis structure is the same as the previous shape, but with an extra lone pair on the central atom. This is actually going to be called seesaw. It looks like this. It's a bit hard to visualize, but you can think of the lone pairs and the F's forming a triangle. So these are actually perpendicular to this plane. So it's a non-planar shape because it has 2 planes. And you don't need to know the bond angles for this. The hybridization is dsp3, which you don't need to know for the exam. And the polarity is polar because these 2 vectors might cancel out, but these 2 will not. They will have a net dipole. Next shape is going to be AX4E2. Same Lewis structure, extra lone pair on the central atom. So it's going to look like this. There's going to be a lone pair vertically above the plane, and there's going to be a lone pair vertically below the plane. These 2 lone pairs are going to repel the outer atoms in a way that they will form a square base around the central atom. So this shape is called square planar. The bond angle between each Cl here is going to be approximately equal to 90 degrees, and the hybridization is D2sp3 because 1, 2, 3, 4, 5, 6 electron regions, but of course you don't need to know that for the exam. Polarity is non-polar, but the ion we've chosen here as an example, ICl4- is polar, but that's just because it's an ion. And the reason it's non-polar is because you draw the vectors, the dipoles. These 2 are going to cancel out. These 2 are going to cancel out. Net dipole is equal to 0, so it's a non-polar shape. Next shape is going to be AX5, an example being PCl5. So you draw the Lewis structure and it looks like this. I want you to kind of imagine it. These 3 Cl's are going to form a triangular base. There's going to be 1 Cl vertically above them. There's going to be 1 Cl vertically below them. So it's going to look like this. It's called trigonal bipyramidal. The bond angle between the Cl's in the base is 120 degrees. The bond angle between the Cl's that are vertically above the plane is 90 degrees. So the bond angle between this Cl and this Cl is 90, this Cl is 90, and this Cl and this Cl is also 90. Same with the one below. This is non-polar because these 3 vectors will cancel out, and then there's one vector going vertically upwards, one going vertically downwards, which will also cancel out, so it's a non-polar shape. Hybridization is dsp3, but you don't need to know that for the exam. Next shape is going to be AX5E, example of this is any halogen bonded to 5 other halogens. Here we've chosen IF5 as an example. So this is what the Lewis structure is going to look like, and this is what the shape is going to look like. These 4 Fs form a square base. This F is going to be vertically above, and the lone pair is going to be vertically below. So this shape is called square pyramidal, if you can kind of visualize that it's a square pyramid, and the bond angle is 90 degrees. This F forms an angle of 90 to all the other Fs, and these Fs, because they're in a square base, form a 90-degree angle to each other. This, of course, is a polar shape because these vectors will cancel out, but this one going vertically upwards will not. And now the last shape, AX6. This is a central atom with 6 outer atoms drawn around it. You can think of it as 2 square pyramids stuck together. So you have a square base, 1 atom vertically above, and 1 atom vertically below. This is called octahedral. The bond angle is 90 degrees everywhere, similar to square pyramidal. Hybridization is D2sp3, and the polarity is nonpolar because all of the dipoles are going to cancel out. The net dipole is going to be equal to 0. So, rules for polarity, the way to tell if a compound is polar or not. First of all, it's polar if it's an ion automatically, regardless of the shape, and it's polar if not all the outer atoms are the same. For example, if we had C bonded to H, and then you had a Cl, this would obviously be polar because the net dipole would not be equal to 0. Otherwise, if these two requirements are not filled, then you can just refer to the shape rules for polarity. Remember that hydrocarbons are always nonpolar, but if an organic molecule has an atom other than C or H, it is polar. For example, alcohols that end with OH and carboxylic acids that end with COOH. So, now we're going to go over types of IMF. I think it's just a small note to mention that intermolecular forces are forces of attraction between different molecules, and intramolecular forces are forces of attraction inside the molecules between the individual atoms. So there are 3 kinds of IMF forces: London dispersion forces, LDF, dipole-dipole, and hydrogen bonds, which are a special kind of dipole-dipole forces. So London dispersion forces are induced forces of attraction between nonpolar molecules, but all molecules have LDF by default. Polar molecules also have dipole-dipole as well, or H bonds if they have H bonds. They are induced forces of attraction. LDF strength depends on 2 things: number of electrons. If you have more electrons, you have a bigger molecule, so you have stronger LDF, and it depends on the shape. So greater surface area, straight chained, stronger LDF. This has to do with the organic molecules. For example, if you have a branched chain, it's going to have weaker LDF than if you have a straight chain. Dipole-dipole, forces of attraction between polar molecules that don't have H bonds, and H bonds are a special kind of dipole-dipole forces found in molecules that have O, N, or F directly bonded to H. This is because of a large difference in electronegativity between H and O, N, or F, because O, N, and F are the 3 most electronegative atoms. So examples of molecules that have H bonding would be HF, H2O, and NH3. Thank you.